Hello, everyone. It is my great pleasure to welcome today my colleague Benoit Meyssignac for this EC lecture on climate change. So let me briefly present Benoit. Benoit is a scientist at the Laboratoire d'études en géophysique et océanographie spatiale, Lagos, in Toulouse, and at the Centre National d'Études Spatiales, CNES, also in Toulouse. Benoit is an engineer from the prestigious École Polytechnique in France, and also from the Institut Supérieur of Aeronautics and Space, well known by French people as SUPAERO. Benoit started his career at CNES, the French Space Center, working on satellite orbits and celestial mechanics, but after a few years, he decided to move to Lagos to prepare a PhD thesis on sea level and climate research. So it was about 10 years ago, and after his PhD, Benoit changed for a new research topic dedicated to understanding the Earth's energy and water cycles at regional and global scales through satellite observation and modeling, with the objective of detecting and attributing anthropogenic and natural forcing factors causing change in this global cycle, that is energy and water cycle. His research on high precision geodetic measurement of the Earth and the energy water reservoir have led to new insight on the response of this global cycle, energy and water cycle, to climate change. And this is an important guide for improvement of climate models that are developed to simulate future climate. Benoit, I should say, is a rising star in this domain. He served as lead author of the IPCC Special Report on Ocean and Cryosphere, published in 2019. In 2017, he received the Christian Le Provost Prize from the French Academy of Science. And in 2021, this year, he received the ESA Earth Observation Excellence Award for his work on geodetic observation to better constrain the Earth's water and energy budget. So, Benoit, the floor is yours, and we are happy to listen to you.
Thank you, Annie. Thank you very much for this very kind introduction. And thank you for giving me the opportunity to present today. I have prepared this talk with Rami Roca, so let me thank as well Rami here for his help. So good afternoon, everybody, or good morning, depending on where you are. In this presentation today, I propose to show you recent developments where space geodesy is used to estimate the Earth's energy imbalance, and by this means to provide observational constraint on the estimate of the global energy budget. Space geodesy is actually renowned for the monitoring of climate change impacts like sea level rise or ice sheet mass loss. And the space geodesy observing system has continuously progressed over the last decades. And now it can be used not only for climate change impacts, but to estimate the small energy imbalance that is at the top of the atmosphere and which is responsible for climate change. This is a kind of game changer because the geodetic observing system was optimized to monitor these impacts like sea level rise and ice sheet mass loss. And now we want to use this observing system in a different way to evaluate the causes for climate change. And so it changes somehow the requirement on the system and the way we use the system, as I will show you. So in this talk, I propose to show how the space geodesy observing system has matured with time and how it can be used now to provide estimate of the Earth's energy imbalance and further constrain the global energy budget. So before starting, just a quick reminder on what is the Earth's energy imbalance and how it is related to the global energy cycle. So the Earth's energy imbalance is at the basis of climate science. It was first introduced by Joseph Fourier in 1827. And Joseph Fourier showed that at equilibrium, the Earth radiates towards space the same amount of energy in visible and infrared as the amount it receives from the sun. The difference between the energy received from the sun and the energy emitted towards space is the Earth's energy imbalance. And Joseph Fourier showed that at equilibrium, this imbalance should be zero. And so with this simple equation between the forcing and the relative response of the Earth, this equation, when it is at equilibrium, should give the surface temperature of the Earth. Rapidly, things appeared more complex. Svante Arrhenius showed in 1895 that there was a greenhouse effect in the atmosphere, and that actually this greenhouse effect was due to the presence of greenhouse gases like water vapor and CO2. And this effect had to be taken into account in the Earth's radiative response. In addition, he showed that under increasing CO2 concentrations due to coal burning, there is a decrease of the Earth's radiative response at the top of the atmosphere, enhanced by the water vapor feedback. This decrease of the Earth's radiative response leads to a positive Earth energy imbalance. And because of this positive Earth energy imbalance, the Earth starts to store energy. And this energy is actually stored for 90% of it in the ocean in the form of heat. In 1965, Mikhail Boudicca and William Sellers showed that the albedo also changed under increasing CO2. And it's another feedback that has to be taken into account, increasing further the complexity of the radiative response of the Earth at the top of the atmosphere. But in the meantime, Boudicca and Sellers showed that for small changes in surface temperature, for changes of a few degrees or so, the radiative response is actually linear with the surface temperature. And this is a nice result because it shows that the radiative response of the Earth can be synthesized by only one parameter, lambda, which is a climate feedback parameter, also known as the inverse of the climate sensitivity. But this picture did not account for the heat convection in the system. And when Syukuro Manabe introduced this term in 1975, he showed that the linear approximation of Boudicca and Sellers still holds at global scale, where there is radiative convective equilibrium. Otherwise, at regional scale, the budget does not hold. Locally, the competition between radiation and convection has to be resolved. And this is possible by resolving the circulation. This is, these results from Manabe led naturally to the development of global circulation models, whose objective is to resolve the circulation and derive locally the energy budget. By resolving locally the energy budget, global circulation models can track the local anomalies in the energy flows that are generated by the global Earth energy imbalance at the top of the atmosphere. And thus, they can estimate the local impact of climate change. Local impacts such as, for example, here, sea level rise, land ice loss, drought, floods, sea ice loss, ocean mass increase, or changes in evaporation, precipitation, or changes in the local surface temperature. It has been now more than 150 years that climate science is actually trying to estimate and understand the relation between the Earth's energy imbalance at the top of the atmosphere and the local impact of climate change. This quest is arguably the center problem of climate change science. And as you can see, the Earth energy imbalance is at the heart of it. In this picture, you can note that many of the impacts of climate change I was citing before actually change the shape of the Earth or its gravity field by moving water masses around in the climate system. This is the case, for example, of land ice loss, which make water mass transfer between land and the ocean. This is also the case of sea level rise, which is changing the shape of the ocean, or the case of floods and droughts, which corresponds to anomalies in the transfer of water between the atmosphere and the continent. So some of these changes can be observed by space geodesy. And this is actually where space geodesy for the first time helped in climate science, essentially by monitoring these impacts of climate change. So in the next slide, I'd like to show how geodesy helped in the monitoring of these impacts. So as you all know, space geodesy started at the same time as the space era on October the 4th in 1957, with the launch of a geodetic mission designed to measure the atmosphere density, which was named Sputnik 1. So quickly after Sputnik 1, followed many geodetic missions. The general purpose of space geodesy was to monitor the Earth's shape and the Earth's gravity field. And actually, two techniques appeared particularly efficient for this objective. Radar satellite altimetry for the monitoring of the Earth's shape, and space gravimetry for the monitoring of the Earth's gravity field. In the following slide, I propose to explore these two techniques, see how they work and the results they provided in recent decades. So first, satellite altimetry. So radar satellite altimetry consists of a radar emitter that is embarked on a spacecraft. The radar emits an impulse towards the sea surface and listens to the echo. The time travel of the echo from the satellite to the surface back to the satellite provides an estimate of the range between the satellite and the water surface. If you add to this range the distance between the satellite and reference orbit, sorry, I do it again, and reference ellipsoid, you can derive the water level with respect to this ellipsoid of reference. So let me show it to you when we get it. And if you get this position, which is the orbit determination, then you get the water level with respect to an ellipsoid of reference. So this technique was presented in detail by Josh Willis in the previous, in an earlier session of the EC Game Changer series. So the accuracy of satellite altimeters depend on both things, on the accuracy of the altimeters, you can see here estimated in gray, in a dark gray, and the accuracy of the orbit determination, estimated here in light gray. After the first test in 1975 with GEO3, radar altimeters showed constant progress, both on the orbit determination and on the radar altimeter. It's in 1992 here that came to the double technological revolution with Uptake Poseidon. For the first time, along with the radar altimeter, was embarked a GPS receiver and a microwave emitter. The GPS receiver enabled to improve significantly the orbit determination, while the microwave emitter provided instantaneous estimates of the water vapor just below the satellite, enabling the correction of the delay in the altimeter pass that is induced by the water content of the atmospheric column. So with this double technological revolution, the overall performance of the system, of the satellite altimeters, increased significantly to levels close to present day level. Now, radar altimeters can measure sea level with an accuracy of 1 to 2 centimeters everywhere on the globe between 82 degrees north and 82 degrees south. When data is averaged globally, the random error of each single measurement is averaged out, leading to a very high accuracy in global mean sea level of a few millimeters and a stability of about plus or minus 0.4 millimeters per year. Thanks to satellite altimetry, the global mean sea level rise that you can see here of 3.4 millimeters per year in response to climate change became visible, and the acceleration in this sea level also became visible, showing a sea level rate of rise close to 2.5 millimeters per year at the beginning of the record, and something closer to 3.5 to 4 millimeters per year at the end of the record. After 30 years of continuous satellite altimetry, the sea level record has reached now an unprecedented level of maturity. The sea level dataset shows a quasi-global coverage of the ocean with a high spatial resolution of about 1/4 of a degree and a high temporal repetitiveness. Global products are available now on a daily basis, and there is a very low ratio of missing or corrupted data. The sea level data is validating against independent in-situ data from type gauges, and the product is also delivered with estimate of the uncertainty at global scale and at local scale as well, which include the temporal correlation of the errors. And the variance covariance matrices are provided such that the errors in any metrics based on sea level can be derived consistently either on the global mean sea level or on the trends that you can see here, or on the acceleration here. The x-axis showing actually the center of the period when we calculate the trend or the acceleration, while the y-axis is showing the length of the period. You can see that the stability of the satellite altimetry record is also very high. There are drifts which are below 0.4 millimeters per year. You can see that over the whole record here of about 30 years, we have 25 years here. We have a drift which is below 0.4 millimeters per year. Satellite altimetry also provides measurement over the ice, not only over the ocean, especially over ice sheets and sea ice. The measurement over the ice is of a lesser quality than over the ocean because part of the radar echo penetrates actually the ice, and the penetration depends on the water content of the ice. So it's very difficult to estimate a priori the level of penetration of the echo. For this reason, the accuracy of the measurements over ice is closer to plus or minus 10 centimeters. But this is enough to provide the first remote sensing estimates of the ice sheet elevation change in response to climate change. In particular, in these regions where in the ablation zones close to the coast, as you've seen on the Antarctic Peninsula, and as you can see now, you will see now on Greenland. In these ablation zones, which are close to the coast, the changes in the elevation are very fast and important. So we can detect them and quantify them with satellite altimetry. You can see them here in those regions which are close to the ocean. Some radar echoes can also be retrieved over lakes and rivers, providing insights on the response of lakes and rivers to climate variability and to anthropogenic activity as well. This has been particularly successful in remote places like in Asia or Africa, where lakes and rivers are poorly monitored with in-situ data. And that's an example I'm showing here with the lakes over Africa. Now, let's have a look to the second technique in space geodesy that enables to monitor the impacts of climate change. So the second technique is space gravimetry. This technique enables to monitor the changes in the Earth's gravity field and further the water mass transfers in the climate system. This is because 98% of the temporal changes in the gravity field on timescales between 1 month and 100 years are actually caused by transfers of water in the climate system. So the space gravimetric technique consists of estimating the motion of a spacecraft or a constellation of spacecraft in response to the gravity field and deduce the gravity field by an inverse method. The accuracy of the method increases when the spacecraft is on a low orbit and when it is equipped with an accelerometer that you can see here in red to estimate and remove the surface forces. The accuracy is further increased when we make a differential measurement, either between two spacecraft or within a single spacecraft. This increases the sensitivity of the instrument. Felix Landerer explained this in details a few weeks ago in an earlier session of the EC Game Changer series. As for radar altimetry, space gravimetry showed constant progress since the launch of the first laser ranging experiment in the 70s. The first improvement has been the launch of CHAMP, which embarked an accelerometer and a GPS receiver. But the accuracy was still limited to see the time variable gravity field. The revolution came with GRACE in 2002 and the monitoring of the relative distance between two satellites. This differential measurement became possible because the satellites were embarking a microwave link and a laser link between the two spacecraft. For the first time, it became possible to measure the gravity field at the accuracy of about 1 millimeter equivalent water height on spatial scales of 300 to 400 kilometers. This accuracy was enough to detect for the first time the mass transport at the Earth's surface in response to climate change. And GRACE provided estimates of the ice mass loss in mountain areas, like you can see here in Himalaya, but also here in Alaska. It also revealed all the dynamics of water storage in drainage basins you can see here around the world. And it shows these dynamics that is mainly a response of changes in precipitation and evaporation generated by the major climate modes of variability like El Nino. You can see here the signature of El Nino, especially in the tropics. GRACE also revealed changes in terrestrial water storage that are linked to direct anthropogenic activity, like groundwater depletion in India, but also in California due to groundwater pumping. And you can also see creation of large water reservoir in China by a dam building, for example. One of the major contributions of GRACE to climate science has been the monitoring of ice sheet mass loss in both Antarctica and Greenland. So for the first time, GRACE and GRACE follow-on enabled precise and complete quantitative estimate of ice sheet mass loss of both Greenland and Antarctica, confirming the massive changes observed by satellite altimetry on Greenland periphery and on the Antarctica Peninsula here. With the estimate of ice sheet mass loss of glaciers mass loss, GRACE and GRACE follow-on showed that land ice was actually responsible for an ocean mass increase that could explain about a third of the sea level rise observed by satellite altimetry. And GRACE and GRACE follow-on enabled also to show that the acceleration you can see in the sea level rise curve is actually due to an acceleration of ice sheet mass loss, mainly Greenland mass loss, but also a small part from Antarctica mass loss. This is consistent with climate model projections, and it is actually very concerning because it confirms that major changes are occurring now in polar ice sheet, and this will continue in the future during centuries. After 20 years of space gravimetry from GRACE, the GRACE record of the global ocean mass of the ice sheet mass loss and glaciers and terrestrial water storage change have reached an unprecedented level of maturity, like satellite altimetry. It shows a global coverage with a low ratio of missing or corrupted data, like altimetry, except at the end of the GRACE mission. There is a validation against altimetry, both radar altimetry and laser altimetry over ice sheets. And there is also an estimate of the uncertainty with ensemble approaches by different groups, which agree and are consistent between the different estimates, which gives confidence in the estimate of the uncertainty. You can see here the different sources for the uncertainty. There are two main sources: the geocenter motion of the Earth, which has a large uncertainty and can play an uncertainty in the total uncertainty of GRACE. And there is also the uncertainty due to the correction of the post-glacial rebound. You can see that the GRACE estimate of the ocean mass and the land water budget shows also a high stability below 0.5 millimeter per year of drift over periods of about 15 years. Okay, so there is another interesting thing about GRACE and Altimetry is that both records are consistent. And I'm showing here how GRACE is consistent with the satellite altimetry record with the closure of the sea level budget, because this is where this is particularly evident. I'm showing here a figure from UNE with the sea level rise observed by satellite altimetry in black here, and the mass loss from ice sheets and from the two ice sheets and from glaciers with the different colors here below. If you add on top of this the thermal expansion of the ocean, which is measured with in situ data from the Argo network that was deployed in 2000, you can sum these different contributions and get the curve here, the red curve, which fits closely to the observed sea level rise by satellite altimetry in black. And the fit is within error bars. I'd like to pause a few seconds and comment on this result, because I think this result is an essential result for both climate science and for geodesy. First, it is essential for climate science because it shows that we have a precise understanding of the causes of current sea level rise. Indeed, with this very good fit between the sum of the contributions and the sea level rise, we have confirmation that all important contributions to sea level rise have been identified, and we can track back in the climate system to the root causes of the present day sea level rise. The second thing is that I think this result is essential for geodesy because it shows that we have a precise control of both the satellite altimetry system and the GRACE system. Indeed, the consistency of both measurements system at the level of a few tenths of millimeter per year. You see that we have a closure of 0.2 plus or minus 0.5. It confirms the high accuracy of both systems and their consistency. And this closure of the sea level budget gives a high degree of confidence in satellite altimetry and GRACE data, and also in Argo data as it is involved in the closure here. This high accuracy of altimetry and GRACE and the high level of confidence in this record that made GRACE and altimetry data a benchmark now to evaluate and validate the capacity of climate models to reproduce climate change impact. For example, GRACE and altimetry are routinely used now in IPCC reports to validate climate models and select the right climate models to constrain their projections of future sea level. I'm showing here an example extracted from the IPCC SROC report, the special report on ocean and cryosphere. And I'm showing here that the models have been actually validated against satellite altimetry and GRACE over the hindcast simulation. And then when they are selected, because they fit nicely GRACE and satellite altimetry, then they're used to generate projections of future sea level change. And this projection is the basis for the risk assessment you can find in IPCC report. And you can see here the famous burning ambers of the risk assessment of the IPCC report with two cases, a case without adaptation and a case with adaptation. So it's just here developed for different coastal communities like the megapoles, the mega cities close to the coast, or for example, Arctic communities. So it really became a benchmark for this climate change impact. So, okay, the assessment of the impacts of climate change and the associated risk is certainly a most important question, especially for society. And we've seen here that space geodesy plays an important role in this aspect. But now, in this presentation, I like to address another question. the question I want to address is, we have this major, highly accurate and consistent observing system of sea level change, mass change, and land ice loss from space geodesy. And the question I want to ask is, can we use it to understand rather the causes for climate change and not only the impact? So to try to understand this energy budget that is responsible for climate change. The essential question in climate science, in climate change science, is to understand the radiative response of the Earth under increasing greenhouse gases emissions, because this radiative response is the primary cause for climate change. So the question I want to address is, can space geodesy and the observing system we've seen just before help to evaluate or maybe to constrain at least this radiative response of the Earth? As space geodesy actually essentially observed the ocean and land surface, and because the radiative response of the Earth is essentially dominated by atmospheric processes, it seems difficult to constrain directly the radiative response of the Earth. However, there is another option. It is to constrain the Earth energy imbalance here. And if we can constrain this Earth energy imbalance, we can provide an indirect constraint on this radiative response through the energy budget that we can see here. This is possible to do because the Earth energy imbalance, 90% of the Earth energy imbalance is actually stored in the ocean. And when it's stored in the ocean, the ocean heat uptake of energy here generates the thermal expansion of the ocean, which is visible by space geodesy, by the observing system I was presenting before. So the ocean, space geodesy should be able to see this thermal expansion of the ocean, to deduce the ocean heat uptake, and then to provide a constraint on the EI, because this ocean heat uptake represents 90% of the Earth energy imbalance. So in the next slide, I want to show you how this is now possible and the way forwards and the directions of research it opens now. So first, the classical approach to estimate the ocean heat uptake in general is to use Argo measurements of the ocean temperature and salinity. And this is possible on a quasi-global basis since 2005 with the deployment of the Argo profiling floats. So those floats are autonomous devices which profile vertically the ocean for temperature and salinity down to 2,000 meter depth. And they send routinely their data to data centers with a satellite communication link. So when we account for all the data from the different Argo floats and all the different sources of uncertainty in Argo, Greg Johnson, in a recent paper from Loeb and Johnson in 2021, find a global ocean heat uptake from Argo floats of 0.71 plus or minus 0.1 watt per square meters over the period 2005-2015. An issue with Argo is that it has a limited sampling of the ocean. The deep ocean below 2,000 meter depth is not sampled or very poorly sampled. There is an effort now to try to sample the deep ocean. There is no measurement in marginal seas and very few measurements also under sea ice. And for the time being, this uncertainty does not account of this problem of sampling of these regions which are not sampled by Argo. There is an alternative approach which is complementary and which has a more global sampling and a higher repetitiveness, but doesn't provide the vertical distribution of heat. It is so this alternative approach is to estimate the total global ocean heat uptake with the sea level budget. So the idea is that we consider the sea level change measured here in black by satellite altimetry, and we remove the ocean mass changes estimated by grays, these different colors, to deduce the blue curve here, which is the thermal expansion of the ocean. And because the thermal expansion of the ocean is linearly related to the global ocean heat uptake, we can derive an independent estimate of the ocean heat uptake. The constant that relates the thermal expansion of the ocean and ocean heat uptake at global scale is called the expansion efficiency of heat. So let me show you an example of how it works with the period 2002 and 2016. So here it's an example where we translate the sea level budget into an Earth energy budget to estimate the Earth energy imbalance with the geodetic method. So you can see here the sea level budget observed over the period 2002-2016 by satellite altimetry and GRACE. So satellite altimetry over this period indicate a sea level rise of 3.53 plus or minus 0.4 millimeter per year, which is indicated here by the black line. We have over the same period an indication of a global ocean mass increase due to land ice loss and changes in terrestrial water storage of 1.83 millimeter per year plus or minus 0.21. And so when we make the difference between both, we find a thermal expansion of the ocean, which is 1.7 millimeter per year. So now we can translate this sea level budget into an energy budget. So the ice mass loss is converted into ice heat uptake with the enthalpy of fusion. And to make an ocean mass increase of 1.83 millimeter per year, we need 0.02 watt per square meters. The thermal expansion of the ocean is translated into ocean heat uptake with the expansion efficiency of heat. And we find that to make an expansion of the ocean of 1.7 plus or minus 0.56 millimeter per year of thermal expansion, we need 0.67 plus or minus 0.22 watt per square meters. If we add on top of this the energy that is needed to warm the continents and to melt sea ice, we find a total Earth energy imbalance of 0.74 plus or minus 0.22 watt per square meters. This result is consistent with the Argo estimate, slightly larger, but not significantly larger, which suggests that actually what Argo is not sampling is not playing an important role for so far. But we have here a very good confidence because we have two different estimates which are independent and they're consistent with each other. Okay, so now we have an estimate of the Earth energy imbalance, and this estimate is robust because we have independent estimate that converge to the same value, and it's pretty accurate. You can see that the uncertainty compared to the total number is quite low. So we can really measure this significant Earth energy imbalance. Now, we can use this estimate of the Earth energy imbalance to constrain the global energy budget and derive specific characteristics of the Earth energy budget. The first idea that comes in mind is to derive an estimate of the climate feedback parameter, lambda, and to derive, of course, an estimate of the climate sensitivity. So that's an exercise that we've done recently. It still has to be published, but I'd like to show you these first results, which are interesting. So we used here we do the classical exercise of the energy budget to derive an estimate of the climate feedback parameter. And then we take the inverse of this climate feedback parameter here, lambda, and multiply by the 2 times forcing in CO2 to get the climate sensitivity to CO2 emissions. So to estimate lambda, we use the current surface temperature estimate and the current forcing estimate and our estimate of the Earth energy imbalance, either with the Altimetry minus GRACE method or with the Argo method. Then we make the difference of the energy budget with respect to the pre-industrial state to derive the climate feedback parameter. And so we find an estimate of the climate sensitivity when we take the inverse of lambda and multiply by 2 times the forcing of CO2. We get a distribution of an estimate of the climate sensitivity with this distribution here. You can see that, as expected, the distribution has a very long tail. This is because we take the inverse, we have an observational constraint on lambda. And because we're taking the inverse of lambda, when you take the inverse, it inflates very much the high values, which corresponds to values of lambda, which are close to 0. Unfortunately, so you see that the results, we have a constraint on the climate sensitivity from Altimetry, Grace, and Argo, which are both very consistent with each other, as expected. We find a climate sensitivity of 3.5 with the 595% range is 1.6 and 20.7. So you see that the constraint from the geodetic system and from Argo is not very strong on the high end of the distribution. And so we don't have any constraint here on the high-end sensitivities. We would need actually to have a much more precise estimate of the Earth energy imbalance, and above all of the forcing due to aerosol. It's mainly aerosols which are doing this long tail. However, the interesting thing here is that we find a low end of the distribution which is at 1.6 Kelvin, and this is interesting because this 1.6 Kelvin shows that today there's a climate sensitivity, very low climate sensitivity, as we used to have from observations, is actually not consistent with the observations from satellite altimetry and Grace. And this confirms that results from climate models over the past decades, which show that climate sensitivity below 1.5 are very unlikely. And so we have here a reconciliation between observations and model estimates. And that's interesting because it's some kind of new insight. So it's quite promising. And in the future, as the record of satellite altimetry and space gravimetry increase, we expect to refine this constraint. And this is interesting because it provides independent estimate based on the satellite record, which is pretty robust compared to other records of old in-situ temperature. Okay, so we have the geodetic approach enables to get an estimate of the Earth energy imbalance, but not only the mean estimate, it provides also an estimate of the time series along time. I'm showing here the time series of the Earth energy imbalance derived from altimetry minus Grace, and with an uncertainty here, which is computed by a propagation of the uncertainty from satellite altimetry and space gravimetry. And you see that this level of uncertainty allows two things. It allows to determine that there are some interannual variations in the Earth energy imbalance. And there is also a trend, which is especially due to a change in 2012 in the Earth energy imbalance. Interestingly, these changes in the trend, well, and especially this, I would say this jump in 2012 is consistent with Argo, and it's also consistent with the CIRES experiment, which measures anomaly in the radiative budget at the top of the atmosphere. And in his recent paper, Norman Loeb finds a trend in Earth energy imbalance that is similar, and he attributed this trend to a PDO shift in the climate system. Now we can use this time series to constrain the global energy budget and the radiative response. And to do so, we use a variational approach, and we use the variational approach of the NASA NewsText project, in which we are involved with our American colleagues. And so in the next slide, I'd like to show you how we can use this time series and put it in a variational approach with other data of the global energy budget to try to constrain this radiative response. And so these different terms of the radiative response of the climate system. So this is so this figure is the depiction of the global energy balance of the Earth. You're now used with this. I've showed many pictures like this. And the numbers you see are the different fluxes and storages of the global energy budget that can be estimated with different sources, essentially space sources, but sometimes we use reanalysis for some terms like the evaporation or the sensible heat flux, which are not available by satellite or not reliably available. The problem in present day, you can see here, is that when observations or reanalysis are used to estimate these different fluxes of the Earth energy budget, well, the energy budget of the planet does not balance. So the sum of these different fluxes, they end up with an ocean heat uptake of 16 watt per square meters. And 60 watt per square meters now, as you've seen in my previous slide, is actually about 1 order of magnitude greater than what we can explain by changes in ocean heat content or in continental and ice heat uptake. And this result, this inconsistency, is independent of the choice of the datasets used. I mean, I'm not showing here other datasets, but you can use many datasets and you would find an imbalance ranging from 10 to 20 watt per square meters, whatever the combination you're using of these datasets. The reason is that most of the flux datasets are derived independently and therefore in the absence of any balance constraint. And this independent development of the different data sets allows structural biases to remain between the product. And it gives rise to these imbalances you can see here when they are recombined together. So the idea of the new text project is to address this problem of conservation of water and energy and inconsistency with the heat uptake. So in a variational framework, all the fluxes are combined together. We are combining them with a general energy budget equation and the water budget equation that you can see in yellow, in orange, and blue here. And both are linked, of course, the water and energy budget with because of the evaporation term that you can see here. Then we enforce the conservation laws in energy and water that you can see here in green. And we enforce this with a variational framework which seek to adjust every flux within their error bars, and they are adjusted in a way that they try to fulfill the conservation of water energy, and also to fulfill another constraint that we provide from satellite altimetry and GRACE, which is the heat uptake into the ocean. So we fix at the value for a heat uptake 0.53 watt per square meters. In the variational framework, the conservation of water and energy is just added as a soft constraint with an objective function J you can see here. You must know that when we find the solution of the variational approach, we find the solution and we weight the solution with the uncertainty of the different fluxes and the different data sets. So uncertainties are absolutely essential to drive, because it's the uncertainties that will drive actually the solution of the variational framework. There are two nice benefits of such an objective approach. It allows for the conservation of water and energy, of course, and also the consistency with the ocean heat uptake that we provide with altimetry and GRACE. But it provides also a metric I'm showing here, which is the goodness of fit. So these metrics can provide us a way to evaluate to which extent the balance between the different fluxes can be achieved within their uncertainties. And so we can determine to which extent these energy fluxes that are measured by different satellites are consistent with the current ocean heat uptake estimate from satellite altimetry and GRACE. I just want to emphasize that uncertainty estimates in this approach are absolutely essential, because that's what will drive the solution of the objective variational framework. In general, the uncertainties are estimated by validation studies locally, by product intercomparisons or sensitivity studies. That's the first step, which is interesting. But we would need, the ideal would to get in the future proper error propagation, which is lacking in general. Note that in the case of the Earth energy imbalance derived from altimetry and gravimetry, the uncertainty estimate is particularly important, because since altimetry and gravimetry is providing a very accurate estimate of the Earth energy imbalance with a very low uncertainty, this uncertainty plays an important role in driving the solution of the optimized solution of the variational framework. And this is the reason why we spend so many time and such a special care in the computation of the uncertainty on altimetry and GRACE. Okay, so here is the result. So You have the initial value in magenta, and in blue you can see the value when we have enforced the conservation of water and energy and the heat uptake in the ocean. So as expected, you can see that now the heat uptake of the ocean that is coming out of the variation framework is very close to the 0.53 watt per square meter that was prescribed by Altimetry and Grace. On a general manner, we find that the optimized energy budget is within the uncertainty of the specified input data sets. So we find that there is an agreement between the data sets and the conservation of flow and energy and water and the ocean heat uptake from Altimetry and Grace within the uncertainty of the different fluxes that are estimated by the different satellites. You can see also here below the expert values for that was provided by different expert estimates from Trenbers and colleagues in 2009 and from Stephens and colleagues in 2012. And the nice thing is that you find there is a good agreement between our estimate, which is objective, compared to this expert estimates. So this is a real promising way to propagate the constraint from satellite altimetry and Grace into the global energy budget of the Earth. Okay, so time is running out. I propose to skip the last 3 slides and get to my conclusion, if you agree. Okay, so in conclusion, satellite altimetry and space gravimetry has provided and is still providing today invaluable contribution to the monitoring of climate change impacts. And this includes the monitoring of course, sea level rise, land ice, ice sheet mass loss, ice thickness, and many others. Now, satellite altimetry and space gravimetry combined together allow to estimate ocean heat content changes and to provide an estimate of the Earth's energy imbalance. And satellite altimetry and space gravimetry yield an estimate of the Earth's energy imbalance of 0.71 watt per square meters, plus or minus 0.2, over the period 2002-2020. And there is confidence in this estimate because it's consistent with the in situ estimate from Argo. We find also that there is a trend in the Earth energy imbalance. That is actually a jump in 2012, and this is consistent with measurements from CRES of the radiative budget at the top of the atmosphere. The Earth energy imbalance from satellite altimetry and space gravimetry can be used to constrain the global energy budget. And the satellite flux datasets that are in general when they are generated in isolation, they yield significant imbalances in the energy budget reconstructions. And these imbalances are too large to provide an accurate tracking of an Earth energy imbalance of only 1 watt per square meters into the system. But we find that if we enforce a posteriori the conservation of water and energy, and the constraint from the Earth energy imbalance derived from satellite altimetry and Grace, we can objectively reintroduce a system into the budget. And we find now that the budget which closes energy, the energy conservation, that respects the energy conservation, the water conservation within their error bars. And we find something which is very close to expert estimations in the past. It's nice because it's an objective method which provides a general view of the energy fluxes. And we see that the use of altimetry and space gravimetry in this approach is particularly important to constrain this regional view. So it's a kind of change of paradigm because usually satellite altimetry and space gravimetry was used for climate change impact. And now we want to use it to estimate this energy budget. And it's a change of paradigm because now the requirements we want to put on satellite altimetry and space gravimetry are slightly different. there are two fundamental things that we need to be able to follow this path where we use satellite altimetry and GRACE in the Earth energy budget. There are two important things that we need to care of. This is the consistency between GRACE and satellite altimetry, and it is the characterization of uncertainties. The consistency should be at the level of a few tenths of watt per square meters if we want to track the changes that are responsible for the EEI, because the Earth energy imbalance is only of 0.7 watt per square meters. And the uncertainty estimate have to be robust to get the right objective optimized solution out of the variational approach. So uncertainties should rely on error propagation in the observing system rather than on expert estimates or sensitivity studies. So in the perspective, in the future, and that will be my last slide, in the future, we would like to improve our estimate of the Earth energy imbalance at the level of plus or minus 0.1 watt per square meters. Because this is the level that we need to analyze typical things like the hiatus or the effect of the hiatus on the climate or the effect of large volcanic eruptions. This is also the level we need if we want to see on the physical system the consequences of mitigation policies at decadal timescales. And we would need also to get down to plus or minus 0.02 watt per square meters per year on the Earth energy imbalance if we want to analyze things like the PDO shift showed by Norman Lobe in 2021. So it drives a new constraint of the level of 0.2 millimeter per year, 0.25 millimeter per year equivalency level on the Space Geodetic observing system. We think that these numbers are possible in the future. I'm showing here an estimate of the uncertainty in satellite altimetry on timescales of 20 years, derived from the actual system, the present day system. And we see that we are, after 20 years, if we consider only recent data, when we are far from TOPEX and JSON1, we get close to 0.2, but we are not really exactly at 0.2. And the reason is that because we have errors in the ITRF, the terrestrial reference frame, and we have also errors at high frequency. But like a small increase in the accuracy of the ITRF of about 10%. And we think that we could better specify the noise in high frequency. That could lead to this kind of 0.2 millimeter per year over 20 years. But we still have work to do, but we think this is reachable in the coming years. As for gravimetry, we are waiting for the next generation missions, especially the MAGIC mission, where there should be two pairs of satellite like GRACE, and we expect with two pairs of satellite like GRACE to be able to get down to this level of uncertainty. And if we get down to this level of uncertainty, then we probably can meet this objective on the Earth energy imbalance. Okay, thank you for your attention. And if you have questions, I will be happy to answer them.
Thank you very much, Benoit, for this interesting presentation. So we have time for questions. So for the participant can either raise their hand or write their question in the chat. So it's up to you. So I don't know if there is still questions. There is one question by Raymond Zaharia, Benoit. I don't know if you see it. If not, I read it. So the question is, what is the meaning of PDO? PDO is Pacific Decadal Oscillation. But
That's
maybe you can comment on what you said, this PDO shift. What does it mean exactly? And what?
Yes, sure. So PDO is a Pacific Decadal Oscillation. So it's a change in one of the climate modes of the climate system, a long-term climate mode. And when this climate mode is changing, surface temperature and the pattern of surface temperature are changing. And along with the pattern of surface temperature, there is also the cloud cover, which is changing. And so the response of cloud, and so the albedo and the relative response of the Earth is changing. And this can change the Earth energy imbalance. And that's what Norman Loeb showed in a recent paper in 2021, showing that the shift that we're observing, that is changing from a positive Pacific decadal oscillation to a negative Pacific decadal oscillation, could explain this difference in the Earth energy imbalance.
There is a question by Jonathan Bamber, but Jonathan, you did not write your question, so maybe you want to ask Jonathan?
Oh, yeah, okay. You can hear me now.
Yes.
Yeah. Oh, well, yeah, I think I just typed it there. Hello, Benoit. Thanks for the fascinating presentation, and hello from quite a chilly Munich. Several times you mentioned this 90% of the EEI is absorbed by the oceans, and I guess I don't really know where that value came from. I presume it comes from GCMs or not, but you know, they have their own biases, and you know, that value, I guess, can't necessarily be a constant because it depends on all kinds of climate feedbacks. And so I just wondered how robust that 90% was. That was question one. And if I may, question two was also altimetry only goes to 60 degrees latitude. So you're missing like the Arctic Ocean and the Southern Ocean. The Arctic Ocean is warming quite a bit faster than, I know it's small, but it's quite a bit faster than.
Yeah.
So those might too.
Yeah. Okay. So the first question about hold on, I forgot. So your first question was about
the 90% that you say is absorbed by the ocean.
So this 90%, so in the past, 90% came, so it was based on GCMs, but there is an estimate from Karina von Schuckmann in 2020 based on observations, which confirm, so we expected 93% from the GCM, and an estimate of the heat uptake in ice made by temperature measurements in the ice, in ice sheets, glaciers, and sea ice, but also temperature of continents in boreholes, shows that actually we're closer to 90% rather than 93%. And so this is based on observations. Now, I'd like to say a comment about this. Have a look to von Schuckmann and colleagues in 2020. This number, also, we don't really know whether it's 93 or 90%. It's a number that is expected to be very constant with time, because what fits this number is the difference of heat capacity between the ocean, the cryosphere, and the continents. And actually, the heat capacity is largely dominated by the ocean, just because about like 2 meters of the ocean make the same heat capacity of the rest of the system. And this heat capacity is not changing with time. Even very small, we don't expect any serious change, even with climate change. So this number is potentially biased, but there is but there is no time variation in this number. So that was for the first question. The second question about altimetry. Yes, so altimetry from Jason and Topex is going to 60 degrees north and 60 degrees south. And you know yourself very well that Sentinel-3 and VSAT and others are going up to 82 degrees north and south. And we use, so to check out what we have in this region, which are covered partly by sea ice, we use sea level in the leads, in the cracks of sea ice. It's less precise, but it gives an idea of the level of sea level rise in these regions. And we find that the impact is very small. We find it's better to use this estimate, which is of a lesser quality, but still we use it. And so we go to, so in winter, of course, there is no many leads higher than 75 degrees north. So in winter, we don't go that up. But in summer we can go quite high. Still, we are missing a part. You're right, and this part we tested with models is expected to be very small, actually.
Okay, Benoit, you have several other questions. Maybe you can, if it is possible, can you give short answers?
Yeah, sure.
So the one question is, when you give the Earth energy imbalance as a global mean, do you consider only ocean areas, or do you scale it over the entire Earth?
So when I give numbers in watt per square meters, I always scale over the whole Earth's surface at 30 kilometers, like CRES, to be consistent with CRES. Now, when we put it in the variation framework, we need to put it like locally, so we have to change that. But the numbers I showed in my presentation are all scaled by the surface of the Earth, the total surface of the Earth at 30 kilometers of altitude, like CRES.
Okay, so thank you. The next question, I don't know if you can read the question, but okay, the next question is about the highest end of century sea level rise. So
what is the highest end of century sea level rise? Not ruled out. Well, the problem is that we cannot rule out in sea levels. There is, you've seen in my presentation, in sea levels, there is a contribution from ice, which has a very small signature in terms of energy. With only 0.02 watt per square meters, you make 1.5 millimeter per year of ocean mass increase. And so we cannot, the energy budget cannot provide any constraint on the sea level because of this ice term, especially ice sheets. With a very low level of energy, you can provide a large sea level rise. And so we cannot provide such a constraint for this reason. Then there is a question from CK.
Two questions from CK.
Yeah, that's true. Hi, CK. So do you have any preliminary explanation to the uneven long period oscillation in your preliminary energy balance evolution? No, not yet. So I think the best. So the best thing to understand the evolution of the Earth energy imbalance. The best way today is definitely to use CRES measurement, because the CRES measurement can break down the Earth energy imbalance observed at the top of the atmosphere into infrared radiation and shortwave radiation, and so you can check out the role of clouds and the role of other feedbacks. And so if you want to have this kind of explanation, I propose you to look at the papers from Norman Loeb, which look into this kind of details. So CRES has this capacity of not getting the mean state of the Earth energy imbalance, but getting the time variable of the Earth energy imbalance, and to break this down into infrared radiation and visible radiation. So it gives insights on this kind of questions. Now, your second question, CK, was, how does one using your NICE method to possibly look back to the past? So we have ideas. So we have ideas on how to look in the past and try to provide a new estimate of the Earth energy imbalance with a method based on geodesy, especially using a sea level budget provided by ANI, for example, over the whole period of satellite altimetry. This would be a first step.
Thank you.
Martin Heimann is saying that the heat capacity of the ocean will diminish with the warming. Yes, that's true. But we're talking about, so this is the change in heat capacity. But so this has to be added to the total heat capacity of the whole ocean down to 6,000 meter depth. So the change is just like negligible, but by many orders of magnitude compared to the total number.
I don't know if there are some other questions. Yes, one question from Giulio Mandorli. You see it?
Yeah, so he's asking why EI is showing an oscillation with period about 2 years. So we have this oscillation at long time scale and about 2 years and longer. And actually one of the primary reasons, so we've not checked out precisely, but I expect El Niño to have an important impact on this. And Norman showed this many times that Niños have an impact on the pattern of clouds in particular. And by changing clouds and also changing the pattern of SST, it changes both the albedo and also the radiative response because of changing the SST. You have also the Planck term of the radiative response is changing as well.
Okay, so I think we will close shortly, but I have a question, if I may.
Yes, sure.
What are the implications of your climate sensitivity estimate from geodesy for climate projection? Can you comment on that shortly?
Say it again. Sorry, you mean implications?
What are the implications of your estimate of your new estimate of the climate sensitivity using geodetic method?
So if you so the climate sensitivity, if you look at the numbers that are provided in the IPCC IR6, it's made by different lines of evidence, and so there are lines of evidence from paleoclimate, which are constraining the high-end sensitivity, lines of evidence from models, which are constraining the processes responsible for climate sensitivity, and they are also constraining the high-end sensitivity. And there are lines of evidence from observations of recent energy budget. And these lines of evidence in the past were using old in-situ data, and they were showing that they were not very constraining on the low end. And now with recent estimates from Sherwood and the estimates we are proposing ourselves, we find that actually low-end climate sensitivity below 1.6 are not actually consistent with the recent energy budget. So what we're providing here is a confirmation of the recent results from Sherwood, who used Argo, that below 1.6, we think it's not consistent with the current energy budget, and so the observations are of GRACE and satellite altimetry.
So this means sorry to interrupt you, but my understanding is that this means that you will, I mean, the climate model, the climate simulation will provide more precise estimates of the temperature increase, let's say by 2100 for different emission scenario.
Yeah. This means that we trust more climate models, because in the past there was a difference between observations and models. Observations tended to show small climate sensitivities below 1.6, and models tended to say below 1.5 the climate sensitivity cannot be. And now we find that we agree with models, and so models, now we tend to have more confidence on models which were already showing that climate sensitivity was probably higher than what we expected. So compared to previous IPCC reports, now we have confidence that the climate sensitivity is probably high. There is no real argument to have low climate sensitivities, and we are going in this direction with satellite altimetry.
So this means that the 2.7 degree temperature increase by the end of this century, given by the last IPCC report, is trustable. It's your conclusion.
Definitely.
Okay.
There is no, we don't find today an observational argument to go against that, which was not the case.
So I think it's time to close, but there is, I think, a last question by Mark Drinkwater. Can you answer that? And then after that, I think we are obliged to close the session.
Okay, so Mark is asking, how important is the mass change in Geoscience International Constellation as a joint endeavor between ESA and ESA to preserve continuity? So that's magic. That was what I was saying in my perspective. The magic, which is the next generation gravity mission after GRACE follow-on, is absolutely essential. First, for continuity, because when we get a longer record, we get a more precise record and a better constraint. And the second thing is that we expect with magic, by getting two pairs to increase the accuracy of the gravity field by GRACE. And if we increase, as we expect, the accuracy of altimetry, we could get better Earth energy imbalance estimate, which makes everything better in terms of physical constraint from observations.
Okay, so I think we have to stop now. Thanks again very much, Benoit, for this very informative and interesting presentation. we learn a lot.
Thank you very much.
Bye-bye.
Bye-bye.